Hey, NA Physics, it's Mr. Neff. Hey, let's talk today about kinetic energy. But before we do, what kind of animal will help you with your leaky pipes? I'll tell you about that at the end of the video. So today we're talking about kinetic energy, which is one of the three main forms of energy associated with work. The three forms of energy that we see associated with work all the time are kinetic energy, gravitational potential energy, and spring potential energy. Now these three are energies that you can easily see. You can see that something's moving fast, you can see something can fall, you can see something can spring back to its original shape. And so we call those mechanical forms of energy. But kinetic energy is the one we cover first because it seems to be the one that is the most important. It's the one that a single object can have on its own, and it's the one that you always see associated with work. And we even have a very important equation called the work energy theorem coming up here very soon. And in the most pure form, we say that work and changing kinetic energy are one and the same. So let's hit that let's hit that kinetic energy right now. So as I say, that highest level of energy, the only type of energy that an object can have on its own is its kinetic energy. And if you said, well, what exactly do you mean by kinetic energy? I would say that it's an energy that an object has because it is moving. It also has to have mass, right? If it's an object, it has mass, but it's an energy that an object has because it is moving. And calculating it is very, very easy. You do half of the mass times the velocity squared. And that product can be done very, very easily, as I want to show you with a couple examples here. Take a look at the first one. An 80-kilogram man is jogging at a velocity of 4 meters per second, and I ask for his kinetic energy. And then I have a 0.1 kilogram baseball, and it has 20 joules of kinetic energy as it passes over the plate. How fast is it moving? So I'm going to ask you to stop the video here, and I want you to try to get numeric answers for both of those. All right, we're back. I hope you have those answers. As you know, kinetic energy is calculated by doing 1/2 the mass times the velocity squared. So if I take half of the mass of the man, half of 80 kilograms, and multiply by the velocity, 4 meters per second, quantity squared, I'm going to get 40 kilograms times 16 meters square per second square, and that's going to come out to 640. Now, the kilogram meter per second squared, everything but that extra meter, is going to be a Newton. And then that Newton times a meter is going to give you the unit of joule. Now, for the baseball, I'll do something similar. I would say that the baseball has that kinetic energy of 20. So how about we go kinetic energy is 1/2 the mass times the velocity squared. Let's solve for velocity. So how about 2 times the kinetic energy divided by the mass, and square root of that would be the velocity. And so 2 times the 20 joules divided by the 0.1 kilogram, and then the square root. 2 times 20, of course, is 40, and then divided by 1/10 is like multiplying by 10, so that's going to be 400. How about the units? The joule is a Newton times a meter, and if I divide that by a kilogram, somebody might be tempted to leave it like that. I'm actually not going to leave it like that. I'm going to say that a Newton is a kilogram meter per second squared. The kilogram will cancel, numerator, denominator, and I'll have meters times meters, or meters squared over second squared, and I'm going to take the square root of that. Square root of 400 is 20. Square root of meters squared per second square is meters per second. Very nice. And if it's okay, I want to try one more example with you. And this one's one I got right from the College Board. And we have a graph here, and you can see its velocity time, and we've seen velocity time many times. It says the graph shows speed as a function of time for an object traveling along a straight horizontal track. And they're asking the change in the kinetic energy of the object over the time interval shown is what? So what we're looking at here is, I know it changes a lot and it's never really holds constant, but all I really care about for the time interval shown is this starting point to this very finishing point. Now that starting point, of course, is no velocity, and we know how important kinetic energy is tied in with velocity, so that if I did 1/2 mv squared here, I'd get 0. Now up to the other side, it wouldn't be that. At the other side, we'd have 1/2 the mass times the velocity squared. So this is a 0.2 kilogram object. I didn't copy that part on, but the mass of this thing is 0.2 kilograms, and then I'm going to take half of 0.2 times that velocity of 5 meters per second squared, and I'm going to end up with 2.5 joules. And so then the change in kinetic energy would be from 0 to 2.5, so that change would just be an increase of 2.5 joules. Now you're going to be surprised, but that seems like a little bit of an obscure question, but it's actually anything but. That kind of question is really, really common because there's a correlation between the change in kinetic energy and this quantity that we're going to talk about in the next video called work, which is whenever a force causes a displacement, that always seems to be coupled with this change in kinetic energy. So more on that to come. And before we do go, as we said, what kind of animal will help you fix your leaky pipes? Well, of course, a seal. See you next time.